Yeah, all set? Are we still connected or somebody got lost? For my short course, I'm asking. I'm not worried about other short courses.
Thank you.
No, I will draw the analogy. It looks like I am in the satsang. You know what is satsang? In human mythology, we have reincarnations. And the God appears in a different incarnation and kill the demon. The purpose is to kill the demon. So here also we are doing the same thing. We have one problem which was mentioned by Daniel. It means he wrote the one problem here on this side, right? And he tried to do it with the unfolding. The same thing did Patricia with Tartar. And I am also trying to do it with the 2S scale. Little bit different what did not little bit, lot different that did by Van Nathan. Yeah. So and in each way a lot different. Yeah. So basically in all the three methods mainly that and the fourth one by multi-scale. So we are killing the same demon with different weapons. And every method has some type of obstacles which we have to overcome, and sometimes in different situations, sometimes one method is suitable, another one is more suitable than other. So if you are connected honestly, if you must remember that what was the reason of the why we have started all this, the drama of 3 lectures, because we were having problem with the weak convergence, right? This was the thing which was general talk. Professor Nandakumaran introduced that this is the root cause of all the discussions, right? The weak derivative was not, weak convergent limit was not able to express the thing embedded into the function. He showed it by this function, right? Sine of x over epsilon, right? Or more generally, f of x over epsilon was converging to the mean of this, right? And this is just a constant, so there is no representation basically of the function. And then we went back and then we re-observed the periodic case, and we understood that we have to somehow incorporate the fast scale into the cost functional and try to redefine the topology and then try to do something, right? Agree? Or lost? Okay, so how did we modify it? We introduced new type of convergence which we called 2S scale convergence, right? And for 2S scale convergence, we saw that we have to choose the test function which has meaning as psi of x over epsilon, where x was the macroscopic thing and x over epsilon was the microscopic, right? Which we modified the convergence using new type of we modified the topology using denoting new type of convergence, and then we understood in the theorems that what was the main theorem which we saw yesterday, that if you have some u epsilon convergence, u epsilon sequence weakly converging to u0 in h1 omega, this implies u epsilon converges to u0 to a scale in L2 omega times y, and we observed that up to the subsequence it was not gradient of u epsilon was converging to gradient of u0 plus gradient y of u1, correct? So this was the term which appeared, which was not present in the weak, right? Agree? Okay. So we observed that something is happening in the 2S scale, something more information we are getting. So did we? So we were supposed to go back and check for this type of function, right? We gained something or not, right? Did we gain? So in the 2S scale convergence, where this will go? I think Daniel tried to answer this question, And he answered it actually. For me, he answered it very well. But can you remember where did he say? Where did it go? In the 2 scale? Where did it go? It went to Fy, right? Fy. 2 scale in L2 x omega times y. Correct? Make sense? So at least here we have some representation of function. Correct? Earlier it was the average, so we are not. It was just a number, nothing else. Okay. So the question is that if we have a function something like that, what will happen? This convergence will work or not? Correct? What was the case here? Here we were having x over epsilon. It means the periodicity was of epsilon order, and so we saw that okay, this is not working. We defined another topology. We saw that okay, this is working. But if a scale is more finer, the periodicity level is more finer, will it work? Will it work? Can unfolding answer this question? Very quickly. Okay. Let's do this, epsilon 1, epsilon 2. Yeah? First of all, you have to understand it physically, and it's not so simple to show that 2 scale won't work. But it won't work. It will again tend to the average part of this with respect to this variable. So again, you have to see here, we have to define 3 scale. Correct? So here we have to choose the test function something like x. Here we chose some test function like f psi x over epsilon, right? Remember? So we have to now go to the 3rd level. Correct? So we have to we can talk about 3 scale, 4 scale, 5 scale, and so on and so forth. Right? So what is the advantage? I should not say this, but this discussion, I will not explain why, but this discussion is leading towards non-periodicity. Okay? But this thing is the job of Professor Vani. Now, but when you will be expert, you will be able to see slowly that this is called iterative homogenization, and you keep on defining multi-scale test functions, and you can approximate non-periodicity, quote under quote, using the iterative homogenization. Quote under quote means a non-periodicity should have a meaning. What do you mean by non-periodic? Periodic has a meaning. Okay, we have a cell placed side by side, construct a material, for example, and think about it. But what is non-periodicity? See, this should have some mathematical meaning, correct? So we are leading this 2 scale, 3 scale, 4 scale. For me, it is going towards that. Okay, so let's come back and try to implement what we learned so far into a scale. For the problem, it means let's start killing that demon which everybody was killing in the classes. Okay, so let's start with the 1 scale, and since my discussion sessions are robbed, so let's make this class as a more like it's the last class of mine, so let's make it more interactive. So let's start with the easy thing, and if we can do it well, we will implement for the end. Let's start with the 1 dimension. If we can do it well, we will implement the idea for n dimension and try to achieve what was achieved by Daniel or by her. So she did it with the expansion method, and he did it with the unfolding. And Patricia did it rocket fast with the Tartars, oscillating functions. Okay, so what was let me write it, since we are mathematicians, we love the format of theorem. So I'm writing what they did in the form of theorem. For given f in h minus 1. If you don't understand h minus 1, you can replace it by L2. L2 means the energy is bounded, it's not infinite. So f in L minus 1, let u epsilon be the solution of the problem of the boundary value problem. So I am writing exactly the same thing what Daniel wrote, but I will write it more in a more mathematical way. Boundary value problem minus divergence of A of x over epsilon, gradient of u epsilon is equal to f in omega, and u epsilon is equal to 0 on boundary, where A x over epsilon means the matrix Aij x over epsilon with matrix Aij is coercive and bounded. It's the same condition which was explained by Daniel. So if you want me to write it again, precisely it is like this: summation ij n aij x lambda I lambda j greater than equal to alpha summation I is equal to 1 to n lambda I square almost everywhere x in Rn, and the second condition was modulus sum of I is equal to 1 to n aij lambda j is equal to 1 to n modulus less than equal to beta I to 1 to n lambda I. Okay, so u epsilon is the solution of this problem, and we want to see how it behaves when epsilon goes to 0. Then we want to show that u epsilon converges to u0 weakly in h1 0 omega, and number 2 we want to and where u0 is the solution, unique solution of the problem boundary value problem equal to f in omega, and u0 is equal to 0 on delta omega. The matrix A0 is equal to Aij0 is constant, elliptic, and given by A0 lambda is equal to mean of A gradient W lambda hat for all lambda in Rn, where W lambda hat is the solution of the problem minus divergence of ay lambda hat is equal to 0 in the sense of distribution. W lambda hat minus lambda y is y periodic, and the mean of this function is 0. Big theorem? Let's start with dimension 1 and try to reabsorb what she did with multi-scale expansion. Yeah, so for this case, for suppose, so we will prove this if we will have time. Otherwise, first of all, let's observe it. Let n is equal to 1. So what is the problem? We have d by dx of some function a of x du u epsilon by dx is equal to f in 0, 1, and u epsilon 0 is equal to u epsilon 1 is equal to 0, and a is some function which is away from constant alpha, which is away from 0, and it is bounded from constant beta. Okay, this is the one dimension version. This looks easy, right, comparatively? Okay, so what she did was she suggested, okay, u epsilon is equal to u0 plus epsilon u x over epsilon, blah, 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 and then this she substituted it, and she tried to observe what was u0 and what was u1, correct? That's what she did, right? Say yes or not? Or you people are disconnected with her? Connection is very important. Okay, so she did. We are not going to do that. We will take the other method of 2 scale. So first of all, let's see what is the weak formulation of this problem. Weak formulation was introduced by her, right? Very precisely. What was the weak formulation of this problem? Anybody want to say something? So this was the weak formulation. So 0, 1, a of x over epsilon. Weak formulation, if I will not write correctly, find u epsilon in h1 0 0 1 a dx ax over epsilon du epsilon dx small dv by dx is equal to integral over 0 to 1 fx u epsilon x dx, vx dx for all v in h1 0. h1 0 means the value of the function on both ends is 0. The values of the function on both ends are 0. Okay, 0 is the meaning that on the boundary is 0. Okay, agree? Who does not agree with me? Okay, so we have this problem, right? And here she substituted u epsilon is equal to blah blah blah. Okay, what we will do, we will use 2 scale. So for that we have to construct using the test function which we learned in the last classes to find v in h1 0 omega. Okay, so let's choose test functions what we learned from the last classes in this format: v0 plus epsilon v0x plus vx is equal to v0x plus epsilon v1 x over epsilon, where v0 is in h1 0 0 1 and v1 is in the d of 0 1 C infinity periodic in y. Okay, if we take A, is y periodic, we can y is equal to 0, 1, we can choose here y is equal to 0, 1. Whatever the reference cell is, I don't care. Okay? Make sense? Yeah? If we take V0 in H1001 and if we take V1 very smooth with compact support in the first variable and second variable if we take a smooth with periodicity, we can construct this. That we learned, right, in the last classes that if we have periodicity, smoothness in one variable and periodicity, we can construct such functions, correct? Agree? So in total it is in H10, correct? It means if I write V as a sum of this type of functions, V will be in H10. So we can choose V as a test function in the weak formulation, correct? Yes or no? Yes? Okay. So let's choose that. So first of all, before choosing, we have to remember that we have to put the derivative, right? We have to put the derivative. So if you calculate derivative of V, what is equal to? Derivative of V is equal to? First term is fine. This is dV0 dx plus what? Plus epsilon d by dx V1 x over epsilon plus d V1 dy x over epsilon. Agree? Make sense? Okay. So now we will substitute this derivative into the weak formulation. If somebody is getting disconnected, just let me know, I will pull you back. Okay? Okay. So if we substitute this, what we get? 0, 1, a of x over epsilon du epsilon by dx and dv. Okay. Okay. So one thing we need to observe before this. In place of v, if we choose u epsilon, what we get? This one, right? You can apply, you can say directly we apply Lax-Milgram lemma, but here we can apply with the properties of A and we can show that u epsilon using Poincare, we can show that this thing is bounded with a constant C, which is independent of epsilon. Make sense? This thing was done in the first lecture also. Even for the n dimension, we are doing just for the one dimension. There is no difference basically. Just the calculation is a bit simpler. That's all. Okay, so it is bounded. What does it mean? V0 is a function in H1 naught. Any function. And V1 is any function in this space. D means C smooth with the compact support. Okay? And here we learn, right? We need at least periodicity in one variable, and we need periodicity because we had to construct X by epsilon. This is the thing we learned, right? So, okay. So, but this thing is clear, right? It is bounded. What does it mean? What does it mean? U epsilon converges to U0 weakly in H1, 0, 1 up to a subsequence. Right? Up to subsequence. So, and this is equivalent to say U epsilon prime. I am not writing E epsilon prime, epsilon double prime. I am consistent with epsilon, but it is going up to the subsequence level. But finally, we will understand that it was actually the full sequence. Okay, but keep in mind that we are going up subsequence, up to subsequence, up to subsequence. Okay? But I will have to explain. I have to explain at the last that why if every, you know this theorem, if every subsequence of the subsequence converges to a point, then whole sequence converges to that point, right? So even if I am going subsequence after subsequence, ultimately the whole sequence will converge. So this thing implies you have, so that's why I'm not writing epsilon prime, epsilon double prime. I'm consistent with the notation. So U epsilon converges to U0 weakly in L201, and U epsilon converges to, okay, here also we can use the theorem which we learned. So we can use directly the theorem. What was the theorem? Anybody remembers? We saw the last time, which I wrote there somewhere, that if we have weak convergence sequence in H1, what will happen in L2, in the L2 scale convergence? Huh? Yeah, so U epsilon converges to U0, 2 scale in L201 times Y, correct? Yes or no? And one more thing was there. What was that? Gradient. In one dimension is derivative, right? Gradient is one dimension is derivative. So du epsilon dx will converge to du0 dx plus du1 by dy. Here you will have partial derivative because u1 is a function of two variables. Still here we have 0, 1, y, but we know that it's a function of just one variable, so I did not care here. But here you have to take care of this u1 x y. Fine. So can we choose this as a test function here and try to pass the limit? This is the job we have to do now. Okay. Can I write directly no, I think it's better if I write like this. So we have 0, 1, and then we have a epsilon, which is a of x over epsilon, du epsilon dx plus into, what is the thing there, derivative of v? dv0 by dx plus epsilon dv1 by dx x over epsilon dx is equal to integral over omega f fv, which is v0 plus epsilon x okay. What? One more? dv of yeah. There's one more term missing. Plus dv1 dy x over epsilon dx. Happy now? Okay, let's pass the limit. What will happen if we pass the limit? if we pass the limit epsilon tends to 0, limit epsilon tends to 0, what we will get? So first term is limit epsilon tends to 0, x over epsilon, du epsilon, dx, dv0, dx plus epsilon 0 1 a of x over epsilon du epsilon dx dv1 dx x over epsilon plus integral 0 1 a x over epsilon du epsilon by dx dv1 dy x over epsilon dx is equal to limit epsilon tends to 0, 0 1 fx v0x plus epsilon v1 x over epsilon correct. Now it's all right. Can you pass the limit? Can anybody help me to pass the limit? I don't know, I forgot everything. How can I pass the limit? Okay, let's focus on the first term. du epsilon by dx, where it converges? Can we apply weak convergence here? Why to take so much pain of applying 2 scale? Can we apply weak convergence? Who says yes? Hands up. I will stop the class after that. Okay, so we cannot apply. Here there is a problem. We have weak convergence sequence, and the multiplication cannot go to the weak. So we have to apply the 2 scale, right? So for the 2 scale we have a space. du epsilon was converging 2 scale to that term, and this function with this we can use as a test function, correct? This with this, correct? So what is the limit? What will be the limit? 1 by norm of y integral over 0 1 y and ay, correct? And du epsilon was du0 dx plus d delta u1 y xy x dx dy, correct? Second term, where it goes? Second term, dv0, sorry, yes, of course, dv0, very good. Yeah, and relax. It's a good that somebody is saying something. Yeah, yeah. So second term, where it will go? This thing is going to 0, so it doesn't matter where it is go, right? Now, if it goes to 1 by epsilon, and if it is in the form of 1 by epsilon, and it is epsilon, the multiply will not go to 0, right? So you have to check where it goes. Okay? You agree? You cannot blindly say that this is epsilon goes to 0, so we don't care where it goes and product will go to 0. You have to check where it goes, or at least you have to check it is bounded, correct? Independent of epsilon. Okay, so again use the 2 scale convergence, so it will converge somewhere, so it has some meaning that epsilon going to 0, this is going to something non-zero, so multiplication will go to 0. I cannot see. First term, I just multiplied it. This one multiplied with this will multiplied with this. Passing to the limit. It's this thing with this I considered as a test function. You remember what was the test function? Psi of x over epsilon, correct? But it can be in the form of psi x into phi of x over epsilon, correct? This test function which we discussed yesterday can have this format, right? Psi 1 of x into psi 2 of x over epsilon, correct? So consider this as a psi 2 and consider this as a psi 1. Okay, and then pass the limit. Make sense? Okay. Now the second term, we observe that it's going to 0. Because by 2s scale, it will converge somewhere, but it doesn't matter because epsilon multiply, it will go to 0. If it diverges, then it's a problem. Okay, the third term. You have 10 seconds to think about third term. Where it will go? Where it will go, the third term? It will go to, again, 0, 1, ay, d, so the derivative is going to du0, dx plus du1 dy, here it is x, xy, 1 by mod of y, y, and then dx dy. Again I forgot the test function. dv1 dy xy dx, correct? Now it's fine, dx dy. Now it's fine? Any doubt so far? Okay, and then here in the second part. In the second part, what we will get? So this term will go to 0, correct? You agree? Because this will converge to v1 xy and fx, and so it is converging sequence. So epsilon multiplied by convergence sequence totally converges to 0. Game over. So this will converge to 0. Where this will converge, there is no epsilon. So fx v0. So integral 0, 1 fx v0x dx. Okay. So finally, we have 1 by mod of y, integral 0, 1, y, ay, du0, dx, x plus derivative of uy, sec to y, xy, dv0, dx, dx dy plus 1 by measure of this 0, 1 y ay du0 dx plus du1 dy x y multiplied by dv1 by dx dx dy is equal to integral 0, 1 fx v0x dx. Okay. So if we club, so this thing is here, right? This thing and this thing we can take the common, and then we can write here dv0 plus dv1 by dx. Where? Y, correct. Correct. Yes. Okay, so finally we have one of norm of y, 0, 1, y, ay, du0, dx over x plus delta u1, delta y, xy multiplied by dv0 dx plus dv1 dy dx dy is equal to integral over 0 to 1 fx v0 x dx. Yeah. Okay. So now let us consider okay, so I want to say something important here. I don't know I can say it or not. But do you know how to define the bilinear forms on the product spaces? So I want to you to imagine that we are defining product D01 C periodic Y. I want to define a bilinear form here to R such that A of UV is equal to 1 by Y 0 1 Y AY du0 dx 1 tawa y xy multiplied with d phi1 d phi1 dx plus d phi2 dy dx dy. So if we define this bilinear form with respect to bilinear form using Lax-Milgram lemma, we can show that this has a solution in this space. Okay? Okay? कुछ पल्ले पड़ा? Huh? Make sense? Can I define a bilinear form here using this type of thing and show that this is a unique with respect to, as we do in the Lax-Milgram thing, right? So here it's like a product type of a space. You have one space, product of space. So each element of here will look like phi1, phi2, where phi1 will come from here and phi2 will come from here. Okay? Okay. So if we define this bilinear form, we can show that it's linear, blah blah blah, is satisfying all the conditions of Lax-Milgram, and we can show that there is it has a unique solution for each f. Okay? So if it has a unique solution, and that unique solution will be U0, U1, correct? So if you remember, U1 was corresponding to a subsequence, correct? So if it has a unique solution, it means your every subsequence of each subsequence is a unique solution of this problem, correct? And since this is a unique solution, so the weak limit is unique, always, correct? If so if you have unique limit, it means whole sequence is converging to U0, U1. And what is the point to notice here, that we did not need any cell function and this for the computation purpose. You have a weak formulation, use FEM, put into the Phoenix routine and get the solution. That's it, over. But what was the problem we were facing in the other cases? That we were having two problems, so we have to solve one problem, feed the data from the another routine, and then solve it there and then get the solution. Correct? Here we don't need to bother about. Here we have a system which, of course, if you will assemble it in the matrix, it's ultimately a matrix if you solve it by FEM. So you don't need to bother about what is your domain is. The Phoenix will take care of it. So in one hit, you can solve the problem. But at that time, what was happening in the multi-X, we were having a cell problem. So you have to solve the cell problem, take the data from there, and feed it there. So you can say, okay, you arrived at a different problem, right? You can say that, right? You arrived at a different problem, you are cheating. It's not the same problem where they reached. I can show you that this is the same problem. Okay. So let's choose. So far so good? Questions, doubt, comments, anything want to say? Who got disconnected? Wi-Fi, whose Wi-Fi is gone? Anybody? No? Okay. Okay, so choose. First of all, let's choose fees. Let's choose phi 1 is equal to 0.
Just a comment here. This is very important point that I didn't develop, and so I'm very happy that he does the following
He told me to do it well. He told me to do it very concretely. Yeah. He's missed my training. Okay. Yeah, so I'm trying to convey that. So is it more or less clear that what was the problem before which we don't have now? Right? We were having two problems at that time. We one cell problem, we have to take the data from there, feed it here in the omega, and then solve it and get the solution. So you were running two programs parallel time to solve it, right? Here you don't need to. It's a simple FEM problem. Directly you can choose the domain 0, 1, and y and apply the Phoenix routine. That's all. Agree? Wi-Fi is there? That she proved. No, first of all, I will try to show you that we are doing the same problem what they did. The difference is here that it's clubbed together. It's a coupled one. Where? Here? Y variable here? Yes, because our domain, you have to put the coercivity here. Here you have x, y, here you have x. So it's not, you see, you do remember the proof of Lax-Milgram, we were proving H1, 0. There was just one space. You have product of a space. That's all. And here I am defining the bilinear form in such a way that you can prove that it's coercive, using the properties of A, that matrix where we started. From the beginning, yeah. So this is very simple. Sorry, it's my mistake. Sorry, it's my mistake. Yeah, that's my point. Wi-Fi should not go. Wi-Fi is the lifeline. Yeah. I'm just sorry. I just did a mistake. A of u, comma. Now I think it's fine, right? Yeah. No, if you have doubt, we can do it later. Yeah, it's fine now, right? Sorry, it was my mistake. You got the right point, because if it multiplies by one term, it's a difficult issue. Yeah. So far so good? So we can prove, so here if we choose one time phi1 is equal to 0 and another time phi2 is equal to 0, what we will get? If we choose phi1 is equal to 0, what we will get? Just let me know. If we choose phi1 is equal to 0, what we will get? Or here v1 and v0. So v0 and v1 is equal to 0. Correct? If one time we will choose v0 is equal to 0, another time we will choose v1 is equal to 0. Okay? What we will get if we choose v0 is equal to 0? So it's clear that it's a problem. It's a weak problem has a solution. A solution in the bilinear form we can use Lakshmigram and tell that we have a unique solution. Correct? So what discussion we were doing of the subsequence, not a problem. Finally we have unique solution, so whole sequence will converge, and that deal was settled. Now you can say that this is a different problem. You were promising that we will draw analogy from the last methods, so it's a cheating. So I'm trying to show that this is actually has the information what we saw earlier, using the multi-scale or Tartar or whatever. Yeah. So for showing that, I'm inviting you to choose v0 is equal to 0 one time and another time v1 is equal to 0. If we choose v0 is equal to 0, what we will get? Anybody can say me. I cannot see, it's very far away. I will just copy, you tell me. 1 over integral 0 1 y ay du0 by dx del u1 by del y, yes, huh? dv1 by dy xy dx dy is equal to 0. Very good. And the second, when we choose v1 is equal to 0, what we will get? Wi-Fi is gone? No. What will get? 1 over norm y 0 1 omega y a of y du0 dx plus du1 dy, and then dv0 dx is equal to integral 0 to 1 f v0. Correct? Okay. Okay, this is equivalent to say, so we will separate it 0 1 y ay du0 dx delta v1 y xy dx dy is equal to minus of 0 1 y ay du1 dy dv1 dy xy dx dy. Yeah, and from here we will get 1 integral 0 1 y ay du0 dx plus du1 dy multiplied by dv0 dx is equal to I want to separate it. How can I separate it? I will take this term this side. Fv0. But why it is appearing? Is something wrong? Okay. So if we try to find a strong form which is satisfied, since V1 is it's any function, right? We chose V1 any function in D of 0, 1, C periodic Y, correct? Any function. So we can see it as a test function, correct? See it as a test function. So what will be the strong formulation of corresponding to this PDE? I want to show that these two are coupled system. I want to show that these two are coupled system whose weak form is this. Whose weak form is this? Not that. His weak form is that. And then you will understand that what the other methods was saying. Well, actually, here also we can go back, and this coupled system is actually one is in the cell and another was using the information coming from the cell. This was the idea with the other methods, right? So we are trying to go back and convert. So here, I told you that we have solved the problem using 2 scale, but it's the same solution as what we got earlier that we need to see. And to show that, I am trying to write that system, weak formulation in a 2 coupled system. Okay, one is in the cell and one is the omega. Okay, got my point? Okay, so to do that, I am choosing V0 is equal to 0 one time and getting one weak form, and I am again choosing V1 is equal to 0 and getting another form. When I choose V1 is equal to V0 is equal to 0, we have one cell problem whose a strong form will look like this. Whose strong form will look like this. Minus divergence of AY plus d by dx du 0 plus plus du1 dy. This thing is equal to 0 in y and y u1 is y periodic, and from the second equation we will have minus divergence of AY here we have divergence with respect to y. My divergence of AY du0 dx plus u1 dx is equal to f in omega and u0 is equal to 0 on delta y. Okay? Huh? Yeah, true. You can write like dy dy. Happy? So Wi-Fi is connected. Yeah? du1 by this one? Yeah, sorry, yes. So this is a equation in omega, and it is using the information of u0, which is coming from here. So u0 is the, it is using the information of u1, which is coming from here, and u0 it is using the data from here. So it's like a coupled system. Making sense? So here, if you observe, this is the periodic, this is your cell problem. Yeah? And this is your main problem. So it was basically, it is the, yeah, if you want, I can arrange a little bit and write notations which she was using omega hat and things. But basically, I want to indicate that you have a cell problem, you are using the information of the cell problem here, and then you are trying to give the solution in omega. Agree? Making sense? Yeah? Okay. So now, if everybody understood this, can we do it for Rn? Integral of? Okay, yeah, good point. Yeah, that is a good point. Yes, perfect. It's a perfect observation. Here, if we take the derivative this side, only y will go and the integral will be here. Correct? 0 to 1 dx. This one? Yes, perfect. Thank you very much. It was the correct, and similarly here also, right? Here it's fine. Here it will be integral with respect to y, right? Yes, here we will have integral with respect to y. If we throw this derivative here we will have y, correct? Yes, first equation we have x as a parameter, and then we have for each x parameter we will have a solution in the cell. You agree? Yes, for each x we have this no, I'm getting confused. One moment. I will have the. So the first one will be minus dy dy. Ay, it is right. Ay, gradient of 0. Yeah, this is fine. And it will be in omega cross y. And the second one, we will have integral over y. Now it's fine. The second one will have the integral. The first one is not. Because we have the source term for each parameter x, we have e as a source, and the second one which is coming from the x. No, the point to convey here is it's a coupled system, and it's exactly the same what you saw in the class. We have a cell problem that is feeding the information into the parent, in the parent equation, parent PDE. Get it or not? We just we throw the derivative from here to here and wrote the strong form. And since this is the derivative with respect to y, that the divergence there, derivative here is with respect to y, and in the second equation, the derivative here is with respect to x. So we have derivative with respect to x. Okay, and the cost function decides that which equation is in which space, omega times y or just y. Even if I'm not doing it alone, I'm clear about it. It means you have to help me. I can help you to form the opinion, but you have to tell me what to do. Should we do it for Rn? It means the calculation here is easy. In Rn, you have to every time do it for the divergence, every time you have to see the interaction between the different coordinates, and that's all. Okay? Should we try? My discussion session is robbed. I cannot do anything. So we have to discuss now. Yeah? Okay. Let's try it for n is equal to for a general n. Okay. I did it for n is equal to 1 first, though it is comparatively easy. It's not easy, comparatively easy, but we can see because we have just one derivative, so we can play with shifting the derivative here and there. Calculation wise, it was comparatively easy, but principally we have to repeat the same discussion what we did now for Rn, and that's all. And there we will have to choose the derivative as the divergence and gradient and so on and so forth. So if you understood the idea, there is one more chance to repeat it for Rn and get it mastered. Yeah? Okay. So now we can compare with the results of Daniel and the result. So we dealt with Professor. We dealt with it. So, yeah. So we will deal you before. No. The idea I'm talking about, that your problem is basically the cell problem and the thing. It is clubbed here together, and you don't need to separate it when you are using to scale. But basically, the information is included. Okay. And for the FEM guys, where are they? FEM guys, you don't need to bother. You just need to feed it in Phoenix. You have all the programs available. At least for the toy problem, Phoenix is still getting developed. Every now and then they have versions. So every now and then they have better routines. But you can write it as a LaTeX if you know Phoenix, and then it does it automatically. Yeah? You don't need to even analyze. Okay. So let's do it for Rn. So for Rn, again, let's write down the weak formulation. What was the weak formulation? Weak formulation was omega A epsilon, which was basically x over epsilon. Gradient U epsilon, very good. Your Wi-Fi is connected. And then gradient V dx is equal to integral. I'm writing integral, but if you take in h minus 1, it will be action. Correct? This is clear to everybody, no? I'm taking more regular function. F V dx. Fx dx. Okay, so again we will choose here that so we can show that V epsilon using Lex Milgram. H1 omega is bounded by C. So we will have U epsilon converges to similarly, exactly the same step. Just the writing style is different. Okay, and the calculation, we will see that little bit more complicated. That's all. And I did it n is equal to 1 so that you people can help me now for a general n, not leaving me alone. Yeah? So U epsilon is bounded, so up to the subsequence, U epsilon will converge to U0 weakly in H10 omega up to a subsequence still denoted. So it's clear that why I'm denoting even the subsequent by epsilon prime, right? So because ultimately we have unique solution. Yeah? Everybody agrees with this? Yeah. It's still denoted by epsilon. So this will imply U epsilon to a scale converges to u epsilon 2 scale converges to u0 2 scale in L2 omega times y. Y por eso gradient of u epsilon will converge to gradient of u0 plus gradient y of u1 2 scale in L2 omega times y. Similar, exactly the same. Earlier we were having derivative, here we have gradient. Exactly the same. Yeah? This is actually we have learned the theorem in the last class for n is equal to n general n, right? So we don't need to worry about this. Yeah? Okay. So now again, this first thing to observe, let's write down in such a way that this thing clubs with this as a test function, right? Because in the 2 scale definition we learned that we have u epsilon multiplied by psi x over epsilon, and then we saw how it behaves. Ah yes, very good. You are not sleeping. Yes, it's n. Okay, so we have to write it down in such a way that it should appear as gradient of u epsilon multiplied by psi of x over epsilon. How can we do that? How can we do that? You just need to write gradient of epsilon a x over epsilon transpose of gradient v dx is equal to integral over omega fx vx dx. Okay? Agree? Can I write this? Who did not do matrix theory? We can write this. Okay. Is equal to, now again we will choose v, again construct v is equal to v0x plus what? What we did in one dimension? Plus epsilon v1 x y. I can tell you what is the regularity, but I think you are smart enough now to understand. V1 will have some L2 type of thing in X. In the second variable, you have continuity, and you will have periodicity, and that's all. Yeah. So that we can x over epsilon. Correct. So V0 is in omega with the complex support. C smooth and complex support. Okay, very nice. So let's plug it in and try to see what happens. Okay. So gradient u epsilon a x over epsilon transport. Okay, what is the gradient of v? V is equal to? Gradient of v is equal to? Gradient of v0 and plus epsilon gradient v1 x over epsilon and gradient I v1 x over epsilon. Nice and healthy. Now let's replace it here. So we have gradient v0 plus epsilon gradient v1 x over epsilon plus gradient y v1 x over epsilon. Okay, and what is equal to? Is equal to what? Is equal to omega f x v0 plus epsilon v1 x over epsilon dx. Okay, so when we pass the limit epsilon tends to 0. What we will get? Okay, let's concentrate on the first term. Okay, first term means this multiplied with this multiplied with this. What we will get? What we will get? Can we pass the weak limit? I am asking the same question. Can we do the weak limit? Who said yes? So we cannot do, because again we have weak convergence here, weak convergence here, together we cannot do that. So we have to go to a scale, and then we have to use the definition of to a scale, which gives us gradient u epsilon goes to gradient u0 plus gradient of y u1 multiplied with gradient v0 plus epsilon term will go to 0. This term we don't bother. I am doing it a little faster. I am not multiplying each term and telling you every detail. Yeah? So this term is 0, correct? Because epsilon is multiplied. Sorry. Yeah, later I will try to recall. Yes, ay transpose gradient v0 plus. Okay, the second term I am saying is going to 0 because the same analogy what we did. We have a bounded sequence, epsilon multiplied, together it will go to 0. The same, exactly the same analogy. In the third term, we will have gradient y v1 xy dx dy. Correct? This thing is equal to what? This thing is equal to integral over omega, integral over y, 1 by mod y, f of x, v0 x dx. So this does not have any meaning. Okay? Make sense? Doubts? Clear to everybody? This is surprising. Okay, so we have this. Can you see this is the same, exactly the same thing what we did for dimension 1. Here we have gradients, and there we were having. So in place of partial derivative, we have gradient with respect to y, and there, yes sir. You want to say something? Okay, so there we were having partial derivative with respect to y. Here we have gradient, and in place of total derivative with respect to x, we are having gradient of u0. Okay, let's try to separate it. So again, you have to first of all observe that this has a unique solution using the same argument. Using the same argument, you can say that this has a unique solution. Analysis does not, in general, not always, in general does not bother about the dimension. Only the complexity of the calculation is here and there. Okay, so should I take it for granted that you people understood that this will have a unique solution, right? And now we will try to separate the two scales. Okay, how can we do that? How can we do that? What we did there? Yes, very nice. V0 is equal to 0, and here we will consider V1 is equal to 0. If V0 is equal to 0, what we will get? If V0 is equal to 0, we will have 1 by arm of y integral y gradient of u0 plus gradient y u1 multiplied by a y transpose gradient of y v1 xy dx dy is equal to 0, correct? V0 is equal to 0, this is 0, and when v1 is equal to 0, what we will get when we have v1 is equal to 0? 1 by omega y gradient of u0 plus gradient y of u1 a y transpose gradient of y v1 xy dx dy is equal to integral over omega fx v0x dx. Okay. Okay, so what we can conclude now? What we can conclude now? So again, if you want, I want to take this thing this side, I will have to take again the transpose, and it will be here. A y transpose, and here also we can write a, oh sorry, without transpose, ay. Correct? Yes, ma'am. If v1 is equal to 0, I did a mistake. That's why. So we have to choose a v0. v0, correct? Now happy? Okay, so now just go back and see what we got in dimension 1 and what we got in dimension n. It's exactly the same, correct? Now, what is the strong form of the solution? What is the strong form of the solution corresponding to this equation? Because your v1 is an arbitrary function in d of omega c periodic y, correct? It's arbitrary function. So what we can say about the strong solution? What we can say about the strong solution, strong PDE, a strong form of the problem? It's a weak form of the problem, right? What is the strong form corresponding to this? Minus divergence of y gradient u0 gradient of ay, and then basically I can do something more. Get out? Okay, I will get out, just 2 minutes. It is independent of x, right? Sorry, y, independent of y. So I can take this term out, leaving ay inside, right? And then we can take this term here and use it as a source. Exactly what we did for dimension 1. Yeah, we can take this term as here, and then we can form a PDE minus divergence of ay of this gradient, and here we will have source term like ay of u0, correct? Yeah. So you can treat x, the parameter of omega, as a parameter, and see this problem as a problem in y, correct? And then here also, similar way, we can form omega a PDE, a strong form of PDE in omega cross y, and we just think to observe is that this is a coupled one. One PDE is in the reference cell, another PDE is in the omega. So it is using the they are interchanging the information all the time. Okay? My time is up. If you have questions, we can discuss it whenever you want. Yeah.